We're doing the physics of harmonics. First of all, we're going to discuss a wave, what a wave looks like. So we can visualize waves to look like a sine wave shape where it goes up and down like a classic wave that you would think a wave would be, like how you would see it in an oscilloscope, which is something that used to measure the visualize sound waves. Now in a wave there are some bits that you can actually label of the shape of the curve. So at the very top point, the highest point, that's what we call the crest. The lowest point is what we call the trough. These 2 points are what we call antinodes, which are the opposite of nodes. So what are nodes? Nodes are where the curve, the wave, cuts the middle, cuts the very center, what we call the equilibrium. And where it's at the equilibrium means at that point in the curve, or that point of the wave, I keep saying curve, at that point of the wave, there is no displacement. In a wave, you can see something called the wavelength, which is how long a section of a wave is until it repeats itself. So it can be a measure from the crest, which is the top of the wave, the highest point, to the next crest, or simply the length between two same points of a graph, how long that section is. That is what we call the wavelength. Then we have got frequency. Frequency is just simply how many times the wave repeats itself in a second. And frequency is measured in a unit called hertz. Yeah, not the car rental company. It's the same spelling, but it's just simply like how many times the wave repeats itself in a second. So maybe it repeats itself 3 times. So it would be 3 hertz. Now frequency and wavelength is related by an equation, which is, the equation is the velocity of the wave equals the frequency times the wavelength, which means if the wavelength becomes longer for a certain value of velocity, then the frequency will be shorter because wavelength increases, so frequency decreases. It's inversely proportionally to each other. So another thing we know about frequency is that the higher the frequency, the more times the wave repeats itself. For a sound wave, the higher pitch the sound would be, and it works in an exponential way, and I'll demonstrate what I mean by that in just a second. So first I'm going to play a note, right? This note, the notation for this note is C3. Okay, now this is C3. I don't know why it's called C3, but it has got a frequency of 130.8 hertz. They just measured it, and you can check it if you want. So there's C3. Now if I go an octave higher, I'm going to do that. So you go. This is an octave higher from there. Now this note's got a frequency of 261.6. This is C4, and this is what we call the middle C. I don't know why it's the middle C, but it is the middle C. So basically the frequency scale works in a way where when you go up an octave, the frequency doubles. So from that will be the double of that. Yeah. Now we can discuss a bit more about nodes. Now on a guitar, when you have a string of guitar, we can say a wave is being sent on the string. And on the guitar, there are 2 like natural nodes. When you play an open string, you just play without anything. There's already 2 nodes on the guitar. There is one here, this bit where we call the nuts, which is that white bit here, and there's got this bit here, which is called the saddle. Now, when you play it, it doesn't take a genius to realize that at those 2 points, the string doesn't actually move. That's why it's a node, because there's no displacement at that point. Now, when you play the open string without anything, when you play like a blank, when you can visualize that wave as only having 2 nodes, when you draw that wave out and you compare it to our original complete wave, you can see that the wave, the length of the string here only represents half of the wavelength. Now that bit of string there is what we call the fundamental mode, and you can express out the frequency at that point as f And you can also work out the notation. We can use the original equation that we have earlier. Velocity equals f lambda. Lambda is the wavelength. F equals v over lambda. And we know that the wavelength of a full string, an open string where we don't press anything, that wavelength is half of the length. So the frequency is going to be v over 2L. 2L because the full wavelength would be when you have double the length of the string. Now is where it gets more interesting. Now we're going to go on to the second mode. Now this is when we start to play a note called the harmonics. On the guitar, what you simply do is you take your finger and you just put it on the string so lightly that you just cause that bit of string to not move. Now you would do it on the 12th fret, like this bar is what we call frets. You would just do it on that line, kind of, and that would create a note on the string because you are preventing that bit of string from moving. So now instead of having just these two notes, you have an extra note here as well. So I'm going to try playing that note and just listen, compare to this, alright? There it is. There you go. There it is. So now when we have got a second mode, we still got the same string, like that. But instead we added an extra note in there. So I'm going to add the extra note in the middle. Now, the wave would have to go through the all the nodes, so the shape instead would look like this. So it would look more like that. And obviously we already know that when we established that this is a wavelength, and we compare it to the original shape, we can also say that this length is one wavelength. So lambda, the wavelength, is the same as the rope length, and we can say the frequency goes to v over L. Now if you compare it to the frequency of the open string, you can write it in terms of that. It will be v over 2L on the inside, and you can take a factor of 2, because 2 cancels out and it would give v over L. So what this means is that the second mode, the frequency of the second mode, is double that of the frequency of the open string. So basically when you're playing the harmonic, the second harmonic, which is on the 12th fret, you get a note that is an octave higher than the original note. So now instead of playing the harmonic halfway from the string, you're going to play it a third of a way from the note, from that bit. So the third of a way, you can use the ruler, but I'm gonna just tell you that it's gonna be on the 7th fret there. If you don't believe me, you can just get your finger out, be like, that is gonna be that all the way to the 7th fret. I can go once and once more, so that means it's gonna be 1 over 3. And if you try to play the harmonic there, wow, that is a B5 compared to an E4 there. That's a B5. And even if you want, rather than coming a third from this way, you can come a third from the other note this way. That'll fall on about the 19th fret if we use our magic ruler. Yeah, it's about there. And if you play it, exactly the same note compared to there and there, same note. And so then we get to the third mode. The nodes, you got 2 nodes. I mean, we only did add 1 node. But when we added 1 node, it kind of makes the other one automatic because the wavelength can't actually like change throughout. And so when you draw the wavelength, it would go up, then we go down there, come there again. And so that's obviously the string length. However, the wavelength, where it repeats there. That would be start of a new unit. So actually, the wavelength is only 2/3 of the way of the length. Then you can write lambda in terms of the length. Lambda is, if you measure it, it's going to be 2/3 of L. If you look carefully enough, you would just realize that. And so the frequency, using the old equation, v over lambda, then v lambda is 2/3 L. So I'm going to write like that, 2/3 L. If you play around with your fractions, you would get 3v over 2L and that is actually 3 times, the frequency of the third mode is 3 times of the original frequency. Then we can, without even doing it at first, you can even predict the fourth mode. So the fourth mode, it would look something like this. The wavelength, they would must like go through all the nodes. That one didn't quite, that's a bad diagram. That would be the length of the string, the original length of the string. However, the wavelength is only half of that now, so we can write that lambda equals half of L. So that means the frequency, if you write out V over 2 would equal to, if you play around with your fractions, you will work out that it's V of 4 times V over 2L, which means it's 4 times the original frequency, the fundamental mode, which means you would expect the sound of the fourth mode to be 2 octaves higher than the original, the primary mode. So obviously by just discussing the maths, you would be able to guess that the next mode, the fourth mode, would fall a quarter of a way from the 2 original nodes. So a fourth of a way is about the 5th fret. Just bear with me with that one. You can get a ruler out, but if you play it, I'm not that good with. Oh, it's on. There. That note, that's an E, but 2 octaves higher than the original notes. And you would expect that because the frequency would be 4 times larger, so that means it would be 2 to the 2 times larger, so 2 frets. So it would be 2 octaves higher than that. You would get that. I can't even play harmonic. So this gives us a statement from what we experimented and stuff, that if the frequency of fundamental mode, we'll call it F, then on the nth mode, the second, third, fourth, etc. mode, the frequency will be a multiple of the original frequency of the fundamental mode. So for our example, we use the open string. We use the first string, the highest note, the highest string, and the fundamental mode is 329.6 Hertz. Now when we go to the second mode, we can calculate that, and it should be double of the fundamental mode. And if we put that on the calculator, I'm going to show you that I'm actually going to do this right now, we get 659.2. That's the next, that's the second mode. And does that match with what we have? Yes, it does, because it's a double, and if you put that sound on a tuner, or you don't even have to put it on the tuner, you can kind of listen it by ear, it's the same note but an octave higher. And that's what we expect when we move from one mode to the other. The thing doubles, and because it doubles, that means an octave to an octave higher. And so if we go on to the third mode, it would be 3 times the fundamental mode. And if you put that on a calculator, you get 988.8 Hertz. But does it match with what we have? This is the sound of 988 Hertz being generated by a computer. Okay, fair enough. And this is the sound of the mode. It sounds the same, doesn't it? So that means it does work. Then you can even go for the fourth mode, and fourth mode would be the fundamental mode times 4, which would come to, I'm doing it right now, so bear with me, which is 1318.4 Hertz. And so that brings us to an end of this video about harmonics. Obviously, that's a guitar technique that I definitely need practice on, but you know, I hope you enjoyed this video. If you like what you see, then subscribe, like the video, favorite it. I don't know what other stuff that they usually say to get more viewers to their channel. And yeah, thank you very much for watching, and I'll hope to see you again soon. Goodbye.